Hello, my name is Adrian Monaghan. Today I'm going to prove that 9 to the n minus 1 is divisible by 8 for all numbers n greater than 0. So we will start off with the belief stage, just going through. We know 9 to the 1 minus 1 is equal to 8. 8 is divisible by 8. 9 squared minus 1 is 80. Down all the way here, 728 is divisible by 8. 9 to the 4th minus 1 is also divisible by 8. So we know that these first four numbers are true, so you can kind of go ahead. We know that there's a good chance that this is going to be true for all numbers. So we'll start with the definition of divisibility. So we know a number n is divisible by x when n is equal to k times x, where n, k, and x are all integers. So a number is divisible by 8 when n is equal to 8 times k. So in this here, 8 is the x and k is still k. So assume that we already know that 9 to the n minus 1 is divisible by 8. So then we can set 9 to the k minus 1 equal to 8 times m, where m is an integer. So because we know this is divisible by 8, and from here we know a number n is divisible by 8 when you can represent n is equal to 8 times the k. We can put this down here, replace the k with the m just for a placeholder. 9 to the k minus 1 is equal to 8 times m. So now we have this. We can rearrange this function to get 9 to the k is equal to 8 times m plus 1. But now for the inductive portion, we need to show that 9 to the k plus 1 minus 1 is also divisible by 8. So we can start with some algebra, rearrange this to get 9 times 9 to the k minus 1. We can substitute this 9 to the k, or we can substitute this whole, or 8 times m plus 1. And for here, we get 9 times 8m plus 1 minus 1. We can distribute it in 72m plus n plus 9 minus 1 to get 72m plus 8. If we remove a factor of 8, we get 8 times 9m plus 1, which is equal to 9 to the k plus 1 minus 1. It's kind of rearranged here. And then we end up with this 9 to the k plus 1 minus 1 is equal to 8 times 9m plus 1. So if we remember from the previous slide, this is, we can substitute this in for n, this in for k. Because m is an integer, we know that this is also an integer. So I know that this function has to be divisible by 8. So now for our proof by induction, our claim p of n for p of n, 9 to the n minus 1 is divisible by 8 for all n greater than 0. So our base case n equals 1, 9 to the 1 minus 1 is equal to 8. 8 is divisible by 8, as 8 times 1 is equal to 8. Everyone knows that. Now consider the inductive hypothesis. For all k, k is greater than 0, and k is an integer, p of k is true. This is pretty much saying that for all integers greater than 0, 9 to the k minus 1 is divisible by 8. So now we know that 9 to the k minus 1 is equal to 8 times m, where m is an integer. I explained this in the last slide, I believe. 8 times n is divisible by 8 by the definition of divisibility, and because 9 to the k minus 1 is also divisible by 8 from the inductive hypothesis. So we can rearrange this like we did before. 9 to the k is equal to 8 times m plus 1. Next slide, inductive step. So now we must show that p to the k plus 1 is true. So p to the k plus 1 is equal to 9 to the k plus 1 minus 1. This is divisible by 8. So when we simplify this, we get 9 times 9 to the k minus 1. We can substitute 9 to the k, this into 9 to the k, where we get 9 times 8m plus 1 minus 1. Simplify it down, we get all the way down to 72m plus 8 like we did before. We can remove an 8, pull out an 8, we get 9 to the k plus 1 minus 1 is equal to 8 times n, 9m plus 1. Since we know m is an integer, we know that 9m plus 1 is also an integer. And since 9m plus 1 is multiplied by 8 by the definition of divisibility, 8 times 9 to the m, 9m plus 1 is divisible by 8, which is equal to 9 to the k plus 1 minus 1. And since we know for p of 1 to be true, and p of k implies p of k plus 1, then p of n is true for all integers n greater than 0. So since we know the base case is true, we assumed this, but this p of k implies p of k plus 1, which is all of this work, then p of n is true for all integers n greater than 0. So our conclusions, we started with the belief stage. We made sure that the predicate was true for the first few integers so that we weren't wasting our time. Then we proved the statement was true for all k plus 1. And then we did the formal proof where we worked it all out, said it formally. So thank you.